let yourself settle in for a moment. Take a slow, deep breath, feeling the air move gently through you, and as you exhale, let any tension from the day drift away like smoke dispersing into the evening sky. Tonight, we're embarking on an extraordinary voyage, a journey through space and time that will carry us from our quiet corner of the galaxy all the way to its blazing, mysterious heart. But this isn't a journey that requires any effort from you. Just close your eyes if you'd like, or let them rest on a distant point and allow the story to unfold around you like a gentle tide washing over sand. Before we begin, if you're finding peace in this cosmic exploration, I'd be grateful if you take a moment to like this video and subscribe to the Science Pillow. Your support helps us continue creating these tranquil journeys through the wonders of science, bringing you calm and curiosity in equal measure. And now, let's begin our voyage to the center of the Milky Way. Setting the scene, our starting point. Picture yourself floating in space, suspended in the infinite darkness, looking out at a universe painted with. But you're not just anywhere in this cosmic ocean. You're here in our solar system, orbiting a medium-sized yellow star we call the Sun, in a relatively quiet neighborhood of our galaxy. From this vantage point, if you could somehow step outside of time and space to view the Milky Way from above, you'd see that we live on the inner edge of a minor spiral arm called the Orion Spur, sometimes known as the Orion Cygnus Arm. This is our home, a tendril of stars and gas stretching about 3,000 light-years wide and extending roughly 20,000 light-years in length. The Orion Spur is where some of the night sky's most familiar sights reside. The Great Orion Nebula, that fuzzy patch visible to the naked eye in the hunter's sword, is here with us in this arm. The Cygnus Rift, that dark slash across the summer Milky Way that ancient peoples imagined as cosmic rivers and roads, marks dust clouds in our local neighborhood. These are the landmarks of our immediate galactic vicinity, the signposts of the region of space we call home. Our Sun sits about 26,000 light-years from the center of the galaxy. To truly grasp what this means, we need to understand the nature of a light-year itself. Light moves faster than anything else in the universe, traveling through the vacuum of space at approximately 186,000 miles every single second. In 1 year, light covers about 5.88 trillion miles. That's the distance we call a light year, and we're sitting 26,000 of them away from the galactic center. Let that sink in for a moment. If you could somehow board a spacecraft that traveled at the speed of light itself, which physics tells us is impossible for anything with mass, your journey to the galactic center would take 26,000 years. All of recorded human civilization, from the first cities in ancient Mesopotamia to the present day, spans only about 6,000 years. You would need more than 4 times the entirety of human history just to make the one-way trip. The photons of light leaving the galactic center right now, racing toward us through the darkness, began their journey when Earth was in the grip of the last ice age, when woolly mammoths still walked the northern continents, and our ancestors were just beginning to develop language. And from our position in the Orion Spur, we're nestled between 2 of the galaxy's more prominent features. Inward from us, closer to the galactic center, lies the Sagittarius Arm, a minor spiral arm rich with star-forming regions. Outward from us, farther from the galactic heart, sweeps the Perseus Arm, one of the galaxy's major spiral arms, a grand structure containing some of the brightest stellar nurseries in our corner of the galaxy. We're in what you might call a galactic suburb, far enough from the dense, chaotic center to enjoy relative peace, but close enough to witness the galaxy's grandeur. The Milky Way itself is a barred spiral galaxy, meaning it has a central bar-shaped structure of stars with spiral arms extending from the ends of that bar. If you could view it from above, you'd see a beautiful pinwheel structure, though not as perfect and symmetric as some spiral galaxies. The Milky Way is a bit messy, a bit irregular, shaped by billions of years of evolution, collisions with smaller galaxies, and the complex dance of gravity and angular momentum. It stretches approximately 100,000 light-years from edge to edge and contains somewhere between 200 billion and 400 billion stars, each one a sun, many hosting their own families of planets. Our galaxy is ancient. It formed roughly 13 billion years ago, just 700 million years or so after the Big Bang itself. The oldest stars in the Milky Way, found in its halo and in globular clusters that orbit far above and below the galactic disk, are among the most ancient objects in the universe. These stars were born when the cosmos was young, when the only elements that existed in abundance were hydrogen and helium, before generations of stars had manufactured the heavier elements through nuclear fusion and scattered them through space in supernova explosions. In contrast, our Sun is a relative youngster, born only about 4.6 billion years ago from a cloud that had already been enriched with those heavy elements, allowing for the formation of rocky planets like Earth. As we prepare to begin our journey inward, let's take a moment to appreciate what we're leaving behind. Earth, that pale blue dot, would quickly shrink to invisibility as we departed. The Moon, our constant companion, would fade from view. The other planets of our solar system, those wandering points of light that have guided human navigation and sparked our imagination for millennia, would blur together with the stellar background. Even the Sun, that blazing furnace that gives us light and life, would eventually become just another star among countless trillions. The journey ahead of us spans incomprehensible distances. 26,000 light-years is a gulf so vast that the human mind can't truly grasp it, but we'll make this journey together, drifting through the darkness, watching the galaxy transform around us as we fall toward its ancient heart. Along the way, we'll witness wonders that challenge our understanding of physics, beauty that transcends description, and violence on scales that dwarf anything in our earthly experience. We'll see the galaxy not as a static snapshot, but as a living, breathing, evolving system, a cosmic ecosystem where stars are born and die, where matter and energy flow and transform, where the very fabric of space and time bends and warps under the influence of gravity. Understanding the Milky Way's structure. Before we embark on our voyage, it helps to understand the structure we'll be traveling through. The Milky Way, like many large galaxies, is organized into several distinct components, each with its own character, its own story to tell. The most obvious component is the galactic disk, that flat, pancake-shaped structure that contains most of the galaxy's stars and gas. The disk is where the spiral arms live, those graceful curves of enhanced star formation that make spiral galaxies so visually striking. Our galaxy's disk is about 100,000 light-years in diameter, but only about 2,000 light-years thick in most places. If you scaled the Milky Way down to the size of the United States, the disk would be thinner than a sheet of paper. Within this disk, astronomers now recognize two major spiral arms and several minor ones. The two major arms are the Perseus arm and the scutum Centaurus arm. These are the dominant structures, the features that would stand out most prominently if you could view the galaxy from another galaxy millions of light years away. They're called major arms because they contain the highest densities of both young, bright blue stars and older red giant stars. They're where the action is, cosmically speaking. Regions of intense star formation, vast clouds of hydrogen glowing with the energy of newborn stars, dense knots of molecular gas collapsing under their own gravity to birth new stellar generations. The minor arms, including the Sagittarius arm and the Norma arm, are less distinct. They don't show the same dramatic overdensity of old stars, though they do contain plenty of young stars and star-forming regions. They're like the secondary threads in a grand cosmic web, less prominent but still crucial to the overall structure. Our own Orion spur falls into this category, though recent observations suggest it might be more substantial than once thought, perhaps even deserving of being called an arm in its own right, rather than just a spur connecting two larger arms. The spiral arms aren't fixed structures. Stars and gas clouds don't stick to them like beads on a wire. Instead, the arms are density waves, regions where the gravitational influence of the galaxy's overall structure causes material to bunch up temporarily. Imagine cars slowing down in a traffic jam, then speeding up again after passing through. The traffic jam itself seems to stay in the same place even though the individual cars are constantly moving through it. That's similar to how spiral arms work. Material enters them, slows down due to the increased gravitational pull, often triggering star formation in the compressed gas, then exits and continues on its orbital path around the galaxy. This is why spiral arms are such prolific star-forming regions. When gas clouds enter the density wave of a spiral arm, they're compressed, increasing their density and temperature. If conditions are right, this compression can trigger the collapse of the cloud under its own gravity, fragmenting it into thousands or millions of clumps that each ignite nuclear fusion and become stars. The brightest, most massive stars, the brilliant blue-white O and B-type stars that can outshine our sun by factors of thousands or even hundreds of thousands, have such short lifespans, sometimes only a few million years, that they never leave the spiral arms where they were born. They live fast and die young, exploding as supernova while still in the neighborhood of their stellar nurseries. That's why the spiral arms look so bright and blue in images of other spiral galaxies. They're lit up by these young, massive, intensely luminous stars. At the center of our galaxy lies something that wasn't understood or even suspected until relatively recently in astronomical history: a supermassive black hole. Actually, this structure is common to most large galaxies. Nearly every galaxy with a significant bulge appears to harbor a supermassive black hole at its core, ranging in mass from millions to billions of times the mass of our Sun. Our galaxy's central black hole, designated Sagittarius A, pronounced Sagittarius A star, weighs in at approximately 4.3 million solar masses. It's massive, but not among the largest known. Some galaxies host black holes that would make Sagittarius A look tiny by comparison. Surrounding the central black hole is the nuclear star cluster, an incredibly dense ball of stars just a few light years across, but containing millions of suns. This is the densest stellar environment in the galaxy, a place where stars are packed so tightly that stellar collisions and close encounters are not just possible, but probable over cosmic timescales. Beyond this inner core lies the galactic bulge, a roughly spherical distribution of stars that swells out from the plane of the disk. The bulge contains mostly older, redder stars and has a quite different character from the disk. Where the disk is dynamic, filled with gas and ongoing star formation, the bulge is more sedate, populated by ancient stars that were born when the galaxy was young. Recent observations have revealed that our galaxy's bulge has an unusual shape. Rather than being a simple sphere or ellipsoid, it's actually X-shaped when viewed edge-on, with arms of stars extending above and below the plane of the disk. This is the signature of what astronomers call a box/peanut bulge, and it's thought to form through the evolution of the galactic bar. The bar itself is a concentration of stars and gas that extends several thousand light years from the galactic center, oriented at an angle of roughly 27 degrees to our line of sight to the center. The bar is a crucial component of the galaxy's structure and evolution. It funnels gas from the outer disk toward the central regions, feeding star formation in the inner galaxy and providing material that can eventually fall all of the way to the central black hole. Bars are common in spiral galaxies, perhaps appearing in as many as 2/3 of disk galaxies in the universe. They're thought to be temporary features on cosmic timescales, forming and dissolving over billions of years as the galaxy evolves, though our Milky Way's bar has likely been stable for several billion years. Beyond the disk and bulge lies the galactic halo, a roughly spherical region extending perhaps 300,000 light-years from the center. The halo is populated by old stars, including those found in globular clusters, ancient balls of hundreds of thousands of stars that orbit the galaxy like satellites. The halo is also where most of the galaxy's dark matter resides. Dark matter is that mysterious substance that we can't see directly, but whose gravitational influence we can detect. It doesn't emit, absorb, or reflect light, but it makes up about 85% of the total matter in the universe. In the Milky Way, dark matter provides the gravitational scaffolding that holds the whole structure together, keeping stars in their orbits and preventing the galaxy from flying apart despite its rapid rotation. The galaxy rotates, but not like a solid wheel. Different parts rotate at different speeds. Near the center, material orbits, quickly whipping around the central black hole in years or decades. In our neighborhood, about halfway out from center to edge, the Sun takes about 225 million years to complete one orbit around the galaxy. We call this a galactic year. Since Earth formed 4.6 billion years ago, our solar system has completed only about 20 orbits around the galaxy. Out in the outermost regions of the disk, the orbital period is even longer, hundreds of millions of years. This differential rotation is what winds up the spiral arms and gives them their characteristic shape. Understanding the interstellar medium that fills the space between stars is crucial to understanding galactic structure. This medium is not uniform. It exists in multiple phases, each with different temperatures, densities, and physical properties. The coldest phase consists of dense molecular clouds where temperatures can drop to just 10 or 20 degrees above absolute zero. These are the stellar nurseries, dark and opaque to visible light, but glowing in radio and infrared wavelengths that can penetrate the dust. Within these clouds, molecules like hydrogen, carbon monoxide, ammonia, and even complex organic compounds exist, protected from the harsh ultraviolet radiation that would dissociate them in more exposed regions. Then there's the cool atomic phase, where hydrogen exists primarily as individual atoms rather than molecules. This phase has temperatures around 100 degrees Kelvin and densities of perhaps 10 to 100 atoms per cubic centimeter. It fills much of the volume of the galactic disk between the densest clouds. This is the phase that produces the famous 21-centimeter line of neutral hydrogen, the radio emission that has allowed astronomers to map the galaxy's structure in such detail. The warm ionized medium exists at temperatures around 8,000 degrees Kelvin, similar to the surface temperature of many stars. Here, ultraviolet radiation from massive stars has ionized the hydrogen, stripping electrons from atoms. This phase fills much of the volume between star-forming regions, creating what astronomers call the diffuse ionized gas. It's invisible to our eyes but glows faintly in certain emission lines that astronomers can detect with specialized instruments. Finally, there's the hot ionized medium, gas heated to temperatures of millions of degrees by supernova shock waves and stellar winds from massive stars. This gas is so hot that it emits X-rays. Despite being incredibly hot, it's also incredibly tenuous, with densities that might be only 1/100th of an atom per cubic centimeter. It fills superbubbles and chimneys in the galactic disk, regions carved out by multiple supernovae in star-forming regions. These hot gases can break out of the disk entirely, fontaining into the halo and creating a circulation pattern where hot gas rises, cools, and falls back to the disk over millions of years. The magnetic field threading through the galaxy adds another layer of complexity. This field is not uniform, but tangled and twisted by the galaxy's differential rotation and by turbulent motions in the gas. The field strength varies but averages around a few microgauss, about 100,000 times weaker than Earth's magnetic field at the surface. Despite being weak, this magnetic field plays crucial roles. It provides support against gravitational collapse in molecular clouds, delaying star formation. It channels the flow of cosmic rays, those high-energy particles that pervade the galaxy. It shapes the structure of the interstellar medium, creating filaments and sheets aligned with field lines. The stars themselves come in an incredible variety. Most numerous are the red dwarfs, dim stars with masses less than half that of the Sun. These misers burn their nuclear fuel so slowly that even the oldest ones, formed when the galaxy was young over 10 billion years ago, are still shining and will continue to do so for trillions of years. They're so faint that not a single one is visible to the naked eye from Earth, despite being the most common type of star in the galaxy, by far. For every bright star you can see in the night sky, there are thousands or millions of red dwarfs too faint to see without telescopes. Then there are stars like the Sun, mid-sized yellow dwarfs, that will shine for about 10 billion years. The Sun is currently about 4.6 billion years old, middle-aged, with another 5 billion years or so of stable hydrogen burning ahead of it before it exhausts its core fuel and begins to evolve off the main sequence. These solar-type stars are less common than red dwarfs, but still numerous enough that there are billions of them in the galaxy. Moving up in mass, we encounter the bright, hot stars. A-type stars that shine white or bluish-white, B-type stars that glow deep blue, and the rare O-type stars, the most massive and luminous of all normal stars. An O-type star might weigh 50 or more times what the Sun weighs and shine with the luminosity of 1,000,000 suns. But such power comes at a cost. These massive stars burn through their nuclear fuel at prodigious rates, living only a few million years before exploding as supernovae. They're the shooting stars of the cosmic timescale, brilliant but brief. There are also the evolved stars, giants that have exhausted the hydrogen in their cores and expanded to enormous sizes as they burn helium and heavier elements in shells around inert cores. Red giants, The fate awaiting the Sun in about 5 billion years can swell to sizes larger than Earth's orbit, their outer layers so tenuous that they're more like a hot vacuum than a solid object, yet glowing with the luminosity of hundreds of suns. Some evolved stars become even more extreme. Supergiants and hypergiants, stars so large that if you placed them at the Sun's location, they'd engulf everything out to Jupiter's orbit or beyond. Betelgeuse, that red star marking the shoulder of Orion, is one such supergiant, about 700 times the diameter of the Sun, and shining with the power of 100,000 suns. The stellar graveyard adds its own exotic population. White dwarfs, those Earth-sized remnants of dead sun-like stars, glowing with stored heat as they slowly cool over billions of years. Neutron stars, the collapsed cores of exploded massive stars, objects so dense that a teaspoon of their material would weigh billions of tons, spinning rapidly and sometimes beaming radiation like cosmic lighthouses. And stellar mass black holes, the most extreme stellar remnants, regions where a few dozen solar masses have collapsed into singularities, surrounded by event horizons only a few kilometers across. As we begin our journey toward the center, we'll be moving through all of these structures, through all these phases of matter, past all these varieties of stars. We'll traverse the disk, passing through spiral arms and the regions between them. We'll watch the star density gradually increase as we approach the bulge, then skyrocket as we near the very center. We'll see the character of the stellar populations change, from the young, bright stars of the spiral arms to the older, redder stars of the bulge, and finally to the extreme environment of the nuclear star cluster and the black hole itself. It's a journey through space, but also through time, through the different epochs and conditions that have shaped our galaxy over its 13 billion year history. Each region we pass through tells part of the story of how galaxies form and evolve, how they recycle matter from stars to gas and back to stars again, enriching each new generation with the heavy elements forged in previous generations, building up the complex chemistry that eventually allows for rocky planets and, perhaps, life. The journey begins through the spiral arms, and so we begin, pushing away from Earth and the Sun, accelerating outward into the dark. For a while, the familiar stars of our nighttime sky would still be recognizable. Sirius, the brightest star in Earth's sky, would remain visible, though it would gradually shift position as our perspective changed. Alpha Centauri, our nearest stellar neighbor at just over 4 light-years away, would slip past. But soon, very soon, in cosmic terms, the familiar patterns would dissolve. The constellations that humans have watched and named for thousands of years, those chance alignments of stars that have guided navigation and inspired mythology, would scatter and reform into unfamiliar patterns as our viewpoint changed. The space between the stars is not truly empty. It's filled with the interstellar medium, a tenuous mix of gas and dust that might seem like a vacuum by any terrestrial standard, but which plays a crucial role in the galaxy's ecology. The density of this material averages about 1 atom per cubic centimeter in the regions between dense clouds, though it can rise to thousands of atoms per cubic centimeter in the molecular clouds where stars are born. For comparison, the air you breathe contains about 10 to the 19 power atoms per cubic centimeter, so even the densest interstellar clouds are fantastically diffused by our everyday standards. Most of this gas, perhaps 70% by mass, is hydrogen, the simplest and most abundant element in the universe. Much of the rest is helium, with only about 2% consisting of heavier elements like carbon, nitrogen, oxygen, and iron. These heavy elements, crucial for forming rocky planets and ultimately for life, were all created inside stars and scattered into space when those stars died. The interstellar medium is thus a repository of the galaxy's chemical evolution, slowly enriched over billions of years as each generation of stars contributes its processed material to the cosmic recycling program. The dust mixed with the gas consists of tiny solid particles, typically less than 1/millionth of a meter across. These grains are made of various materials: silicates, similar to sand, carbon in forms including graphite and complex organic molecules, and ices of water, ammonia, and methane. Despite being tiny, these dust grains have an enormous influence on the appearance of the galaxy. They scatter and absorb light, particularly blue and ultraviolet light, causing distant objects to appear redder than they actually are and blocking our optical view of much of the galaxy. The beautiful dark lanes, visible in images of edge-on spiral galaxies, are not regions empty of stars, but rather regions where dust blocks the light of stars behind them. As we journey inward from the Orion Spur, we first encounter increasing numbers of young star clusters. These are associations of stars that were born together from the same molecular cloud, still loosely bound by their mutual gravity. Some contain just a few dozen stars, while others harbor thousands. Many of these clusters will eventually disperse, their member stars gradually drifting apart over hundreds of millions of years until they're indistinguishable from the general stellar population. But some, particularly the more massive clusters with hundreds or thousands of stars, will remain bound for much longer, even for the lifetime of the galaxy. The stars in these young clusters are diverse. There are the hot, blue O and B type stars, giants, that can be 20 or more times the mass of our Sun and shine with the luminosity of hundreds of thousands of suns. These are the stars that dominate the visible light from star-forming regions, but they're actually quite rare. For every O-type star, there might be thousands of smaller stars, like our Sun or the cooler, dimmer K&M type red dwarfs. The distribution of stellar masses at birth follows a pattern called the initial mass function, heavily favoring low-mass stars. This is fortunate for the galaxy because low-mass stars are incredibly long-lived. An M-type red dwarf with only 1/10 of the Sun's mass can shine for trillions of years, far longer than the current age of the universe. In contrast, those brilliant O-type giants burn through their nuclear fuel in just a few million years, living fast and dying spectacularly in supernova explosions. We pass through regions of glowing hydrogen, vast clouds lit from within by the ultraviolet radiation of newborn massive stars. This process, called ionization, strips electrons from hydrogen atoms, and when those electrons recombine with the nuclei, they emit light at specific wavelengths, giving these regions their characteristic red glow in photographs. The largest of these HII regions, as astronomers call them, can be hundreds of light years across and contain enough material to make millions of stars. They're sites of intense activity, with stellar winds from massive young stars and shock waves from supernovae stirring up the gas, triggering new waves of star formation in a process that can sustain itself for millions of years. The journey through our local spiral arm features takes hundreds of years, even at our imagined faster-than-light speed. We pass stellar nurseries like the Orion Nebula, though from our new perspective, it would look quite different from the familiar images taken from Earth. We'd see it in 3 dimensions, recognizing it not as a flat projection on the sky, but as a true cloud of gas and young stars with depth and structure. Behind it, we might glimpse the darker, denser molecular clouds where future generations of stars are gestating, cores of cold gas and dust slowly collapsing under their own gravity. Not yet hot enough to ignite nuclear fusion, but destined to become stars in another few 100,000 years. Between the bright, active regions of star formation lie darker expanses, cold molecular clouds where the temperature hovers just a few degrees above absolute zero. These clouds are the birthplaces of stars, but in their quiescent state, before star formation begins, they're dark and forbidding. The gas is so cold that most of it has condensed into molecules, hydrogen molecules, carbon monoxide, water, ammonia, methanol, and hundreds of other compounds, some of which are the building blocks of life. Radio telescopes have revealed a rich chemistry in these clouds, with complex organic molecules forming in the cold, dark conditions through processes we're still working to understand. After what would feel like an eternity, even in our accelerated journey, we begin to notice the Sagittarius arm approaching. The stellar density increases slightly. We encounter more young stars, more star-forming regions, more of those brilliant blue giants that mark active spiral arms. The Sagittarius arm, while classified as a minor arm, is still a substantial feature, containing numerous star-forming complexes and dense molecular clouds. It's closer to the galactic center than our starting point, and as we pass through it, we're making real progress on our journey inward. The stars here are still mostly population I stars, as astronomers call them. These are relatively young stars, formed within the last few billion years from gas that had already been enriched with heavy elements by previous generations of stars. They follow roughly circular orbits around the galaxy, concentrated in the thin disk. Population I stars like our Sun contain a few percent heavy elements, enough to allow for the formation of rocky planets. In contrast, the oldest stars in the galaxy, called population II stars, contain almost no heavy elements at all, born from gas that was merely pure hydrogen and helium. We'll encounter more of these ancient stars as we penetrate deeper toward the galactic center, where the oldest parts of the galaxy reside. As we traverse the Sagittarius arm and move into the interarm region beyond it, we notice the environment changing. The density of young stars decreases. The bright OB associations thin out. The star formation rate drops. Interarm regions are less conducive to star formation, lacking the compression and triggering that density waves provide. But they're not devoid of interest. Here we find older star clusters, open clusters whose bright, massive members have long since died, leaving behind populations of sun-like stars and red dwarfs that will continue shining for billions more years. We find the remnants of past supernovae, expanding shells of gas enriched with the heavy elements forged in the exploded star's core, spreading those elements through the interstellar medium, where they'll be incorporated into future generations of stars and planets. The journey through these outer regions of the galaxy might seem monotonous if described in astronomical terms, but the reality would be anything but. Each star we pass is unique, potentially hosting its own system of planets, perhaps even harboring life. Each cloud of gas and dust is sculpted by winds and radiation into unique, beautiful structures. If we had time to stop and explore, we could spend lifetimes in each region, cataloging stars, mapping gas clouds, studying the intricate interplay of gravity, radiation, and magnetic fields that shapes the galaxy's evolution. But our destination pulls us forward, that bright beacon at the galaxy's heart, growing slowly brighter as we fall toward it through the years and centuries of our journey. As the journey continues, we notice more dramatic changes in our environment. The frequency of massive stars increases as we pass through denser regions of spiral arms. These stellar giants, with their intense radiation and powerful winds, dominate their surroundings in ways that smaller stars never could. A single O-type star pumps out enough ultraviolet radiation to ionize the gas in a sphere hundreds of light years across, creating those glowing HII regions that mark star-forming regions from across the galaxy. The stellar wind from such a star, driven by the intense radiation pressure, can strip away millions of solar masses of material over the star's brief lifetime, enriching the surrounding interstellar medium with partially processed elements from the star's atmosphere. We would witness the complex ecology of stellar feedback, the process by which stars influence their environment. Massive young stars don't just shine passively. They actively reshape their natal clouds through radiation pressure, photoionization, and stellar winds. This feedback can have contradictory effects. It disperses and disrupts the molecular clouds that gave birth to the stars, shutting down star formation in the immediate vicinity. But the shock waves and compressed gas at the edges of the disrupted clouds can trigger new collapse elsewhere, propagating star formation through the cloud in a complex, self-regulating process. When a massive star finally exhausts its nuclear fuel and explodes as a supernova, the effects magnify enormously. The explosion releases as much energy in a few seconds as the sun will emit over its entire 10 billion year lifetime. The blast wave expands outward at thousands of kilometers per second, sweeping up interstellar gas and compressing it. This compressed gas can cool and collapse, forming new molecular clouds and eventually new stars. The explosion also injects heavy elements into the interstellar medium: oxygen, silicon, sulfur, calcium, iron, and all the other elements up to and including uranium, all forged in the intense conditions of the supernova itself or in the nuclear burning that preceded it. These elements mix with the pristine hydrogen and helium, enriching future generations of stars with the raw materials for rocky planets and, ultimately, life. We'd pass supernova remnants at various stages of evolution. Young remnants, only decades or centuries old, still show the structure of the expanding blast wave, a glowing shell of shock-heated gas expanding into the surrounding medium at thousands of kilometers per second. Inside the shell, in some cases, we might glimpse the neutron star left behind by the explosion. Spinning rapidly, its intense magnetic field channeling beams of radiation that sweep across space like lighthouse beams. These are the pulsars, discovered accidentally by radio astronomers in 1967, and initially so mysterious that some thought they might be signals from alien civilizations. In reality, they're among the most extreme natural objects in the universe. City-sized spheres of matter compressed to nuclear densities, single atomic nuclei the size of Manhattan, spinning tens or even hundreds of times per second. Older supernova remnants, thousands of years after the explosion, have expanded and cooled. The distinct shell structure has broken up, mixing with the general interstellar medium. The heavy elements have dispersed, becoming part of the chemical reservoir from which future stars will form. In a few tens of thousands of years, even the largest supernova remnants fade and merge with the background, leaving only faint wisps of gas, enriched patches in the interstellar medium, and perhaps a lonely neutron star or black hole traveling through space, the sole survivor of what was once a brilliant star. The journey would also take us through regions influenced by stellar clusters, young open clusters, containing hundreds or thousands of stars all born together dominate their regions of space. The combined radiation from all their massive members creates enormous ionized bubbles, sometimes called superb bubbles, that can be hundreds of light years across. Multiple supernovae from the cluster's most massive members, going off over a span of a few million years, drive these bubbles even larger, creating hot, tenuous cavities in the interstellar medium. The pressure from these superbubbles can compress surrounding molecular clouds, potentially triggering the formation of new star clusters and perpetuating a cycle of star formation that can last for tens of millions of years. Older clusters, having lost their most massive members to supernovae, are quieter but still distinctive features of the galactic landscape. Their stars, now mostly sun-like and smaller, form identifiable groupings moving together through space over hundreds of millions of years. Gravitational encounters with passing molecular clouds and the differential rotation of the galaxy gradually pull these clusters apart, dispersing their member stars into the general field population. But for a while, they remain coherent structures, small islands of shared history in the vast ocean of the galactic disk. We'd also encounter the remnants of ancient stellar populations that no longer exist as coherent structures. Stellar streams, long arcs of stars wrapping around the galaxy, mark the tidal disruption of globular clusters and dwarf galaxies. These streams can be hundreds of thousands of light years long, but only a few thousand light years wide, like rivers of stars flowing through the halo. By studying their positions and motions, astronomers can reconstruct the orbital history of the clusters and galaxies that gave rise to them, building up a picture of the Milky Way's accretion history, the mergers and acquisitions through which it has grown over billions of years. The dust lanes we pass through would create spectacular visual effects, particularly if viewed from certain angles with background stars. The dust doesn't absorb all light equally. It's most effective at blocking blue and ultraviolet light, allowing longer wavelengths like red and infrared to pass through more easily. This is why distant stars behind dust clouds appear reddened. And it's why interstellar dust creates those beautiful dark lanes in images of edge-on galaxies. From inside a dust cloud, the view in visible light might be dimmed and reddened, but infrared eyes would pierce through, revealing the stellar background and perhaps the warm glow of dust itself. Heated by starlight and re-radiating in the infrared, some dust clouds would be spectacular in their own right. The reflection nebulae, where dust scatters the light of nearby bright stars, creating those ethereal blue glows seen in images of regions like the Pleiades cluster. The dark nebulae, opaque clouds silhouetted against brighter backgrounds, like the famous Horsehead Nebula or the dark patches in the Cygnus Milky Way. These structures aren't truly empty or dark. They're simply so dense with dust that visible light can't penetrate. In infrared or radio wavelengths, they glow with emission from the dust and gas, revealing their structure and composition. As we continue our inward journey, the transitions between different galactic components would become more noticeable. The gaps between spiral arms would appear as regions of lower stellar density, and reduced star formation, though by no means empty or devoid of interest. The density waves that create spiral arms also create interarm regions where the density is lower than average, and it's through understanding both the arms and the regions between them that astronomers have built up the picture of spiral density waves propagating through the galaxy. The journey inward is also a journey back in cosmic time, in a sense. The outer disk contains primarily younger populations of stars, with active star formation and recent enrichment in heavy elements. As we move inward, we encounter more mixed populations. The inner disk and the bulge contain stars of all ages, from very old population II stars formed in the galaxy's youth to relatively young stars born within the last billion years. This mixing of ages tells us about the galaxy's assembly history and its ongoing evolution, the hazards and wonders of deep space. As we journey deeper into the galaxy, we need to understand that this voyage, while presented here as peaceful and contemplative, would in reality be fraught with extraordinary dangers. The interstellar environment, so sparse and tenuous by terrestrial standards, becomes a hazardous obstacle course when traversed at the kind of velocities interstellar travel would require. The first and perhaps most insidious danger is radiation. Space is awash with it. From multiple sources, there's the cosmic microwave background, that faint echo of the Big Bang that fills all of space with photons that have been traveling for nearly 14 billion years, redshifted by the expansion of the universe from their original high-energy gamma rays down to microwave wavelengths. This background radiation is harmless, but other forms are not. Galactic cosmic rays, despite their name, are not rays at all, but particles, mostly protons, with a small component of heavier atomic nuclei, all moving at relativistic speeds, approaching the speed of light. These particles are accelerated by the shock waves from supernova explosions and other violent astrophysical events. When one of these particles strikes living tissue, it doesn't just pass through cleanly. It's moving so fast that it creates a cascade of secondary particles as it tears through atoms, leaving a trail of damage in its wake. A single, heavy cosmic ray nucleus passing through a cell nucleus can shred DNA, potentially causing mutations or cell death. The sun provides some protection from cosmic rays by generating a magnetic field that pervades the solar system, deflecting many incoming particles. But venture outside this protective bubble, called the heliosphere, and the flux of cosmic rays increases. Deep space travelers would be bombarded constantly by these particles. Over months or years of exposure, the cumulative effects would be significant. Increased cancer risk, potential damage to the central nervous system, cardiovascular effects, and possibly accelerated aging. Even with shielding, which adds mass and therefore cost to any spacecraft, the radiation environment of interstellar space poses serious challenges. Then there are the particles of the interstellar medium itself. At normal speeds, these pose no threat. But if you're traveling at even a modest fraction of light speed, say 10 or 20%, these stationary hydrogen atoms become a hazard. From the perspective of the spacecraft, each hydrogen atom is a cosmic bullet coming at you at tremendous velocity. The kinetic energy of impact can be enormous. These atoms would slam into the spacecraft's hull with enough energy to generate radiation, produce secondary particles, and heat the structure. At very high velocities approaching the speed of light, the interstellar medium itself becomes an intense radiation hazard, potentially delivering lethal doses in seconds or minutes. Dust grains, while far less numerous than individual atoms, pose an even greater danger. A dust grain might be only a micron across, but at relativistic speeds, it carries tremendous energy. The impact of even a small grain could pierce a spacecraft hull. A grain a millimeter across would hit with the force of a bomb. This is why realistic interstellar mission concepts include massive forward shields, thick slabs of material, or maybe electromagnetic deflector systems to push particles out of the path. These shields would need to be constantly regenerated or replenished, as the erosion from the constant bombardment of particles would gradually wear them away. Gravitational fields, while less immediately dangerous than radiation, also pose challenges. As we approach, massive objects like stars or, eventually, the supermassive black hole at the galactic center, the gravitational gradients become steeper. Tidal forces increase. These are the differential forces that arise because gravity gets stronger closer to a massive object. The near side of a spacecraft would feel stronger gravity than the far side trying to stretch it. Near a normal star, these forces are negligible, but near a black hole, they can become extreme. There's also the more subtle effect of gravitational time dilation. According to Einstein's theory of general relativity, time runs slower in stronger gravitational fields. This effect is small near Earth, where atomic clocks on satellites have to be adjusted for it, but it becomes significant near very massive objects. Deep in a gravitational well, time itself moves more slowly compared to someone far away. This would create challenges for coordinating missions and staying in contact with the home world, as the passage of time would literally be different for travelers in different gravitational environments. But the journey would not be solely defined by hazards. The wonders we'd witness would be beyond imagining. We'd pass through nebulae, those glowing clouds of gas that appear as faint, fuzzy patches in telescopes, but which, seen from within, would surround us with ghostly light, vast cathedrals of cosmic architecture shaped by the winds and radiation from nearby stars. Some nebulae glow with the red light of ionized hydrogen, others with the green light of doubly ionized oxygen. Some are blue, their light scattered by dust grains in the same way Earth's atmosphere scatters sunlight to make the sky blue. We'd witnessed the birth of stars, seeing the collapse of molecular cloud cores in real time if we had the patience to watch for thousands of years, or at least seeing the various stages of star formation laid out before us. We'd see dense cores just beginning to collapse, young protostars still gathering mass from their surrounding disks, and newly formed stars just breaking free from their birth cocoons, their light beginning to illuminate and ionize the surrounding gas. We'd see stars die too, not in real time, as a star's life is too long even for our extended journey, but we'd encounter the remnants, planetary nebulae, those beautiful symmetric shells of gas expelled by dying sun-like stars, glowing with the ultraviolet radiation from the hot white dwarf core left behind. We'd see supernova, remnants, the blast waves from exploded massive stars still expanding through space decades or centuries after the explosion, their shock-heated gas glowing in X-rays in visible light, their interiors seeded with heavy elements from silicon to uranium, all forged in the intense conditions of the supernova itself. We'd pass through star clusters of various ages and types, young open clusters, loose associations of hundreds or thousands of stars born together, still containing some of the gas and dust from their birth cloud, with those brilliant blue giant stars still shining. Middle-aged clusters where the most massive stars have already died, leaving populations of sun-like stars and smaller red dwarfs. Ancient globular clusters, balls of hundreds of thousands of stars, all born within a few million years. When the galaxy was young, their most massive stars long dead, their populations dominated by old red giants and white dwarf remnants, all following complex orbital paths within the cluster's deep gravitational well. We'd witness the effects of stellar winds and radiation pressure, seeing how massive stars sculpt their surroundings, carving bubbles and cavities in the interstellar medium, compressing gas into dense shells that might trigger new star formation. We'd see binary star systems, stars locked in gravitational embraces, orbiting each other, sometimes so close that material flows from one star to the other through the point where their gravitational fields balance. In extreme cases, we might witness a compact object, like a white dwarf or neutron star, pulling material from a companion, heating it to millions of degrees, and causing it to emit intense X-rays. The magnetic fields threading through the galaxy, while invisible to the eye, would reveal themselves through their effects. We'd see how they channel the flow of cosmic rays, how they shape the clouds of ionized gas, how they launch jets of material from forming stars and accreting black holes. These fields are tangled and twisted by the galaxy's rotation and by the turbulent motions of the gas, creating a complex, dynamic structure that plays a crucial role in the galaxy's evolution, but which is incredibly difficult to map from our limited viewpoint on Earth. As we continue inward, crossing through more spiral arms and interarm regions, always moving toward that brightening glow at the galaxy's heart, we'd begin to notice the gradual increase in stellar density. At first, it would be subtle, a slight increase in the number of stars visible at any given time, a shortening of the average distance to the nearest star. But it would be persistent, accumulating as we drew closer to the center until, eventually, it would be unmistakable. We're approaching the galactic bulge, that spheroidal concentration of stars that marks the galaxy's ancient heart. Approaching the galactic bulge, the transition from the thin disk to the bulge is gradual. There's no sharp boundary, no line in space where one ends and the other begins. But as we draw within perhaps 10,000 light-years of the center, the change in character becomes apparent. The stellar populations shift. The young, blue population eye stars that dominated the disk become rarer. In their place, we encounter more and more older stars, orange K-type giants, ancient population 2 stars that contain barely any heavy elements at all. This makes sense when you understand the bulge's history. The bulge formed when the galaxy was young, perhaps within the first billion years after the Big Bang, through some combination of early intense star formation and the merger of the proto-galactic fragments that were coming together to build the Milky Way. The stars formed during this epoch had little access to heavy elements because not enough time had passed for multiple generations of stars to have lived and died and enriched the gas. So, the bulge stars are metal poor, as astronomers say, though they mean something specific by metal. Anything heavier than helium, the bulge is also kinematically distinct from the disk. Where disk stars follow roughly circular orbits around the galaxy, bulge stars follow a more diverse range of orbital paths. Some orbit in the plane of the disk, but many move on tilted orbits, spending part of their time above the disk and part below. Some orbits are highly elliptical, carrying stars from the innermost regions out into the disk and back again. This random motion, contrasting with the orderly rotation of the disk, gives the bulge its spheroidal shape. Recent observations have revealed that the Milky Way's bulge is not a simple sphere or ellipsoid. It's actually box-shaped or peanut-shaped when viewed edge-on, with extensions above and below the plane of the disk, creating an X-like structure. This shape is thought to arise from the vertical resonance of the galactic bar. As stars orbit in the barred potential, certain orbits become unstable and pump material out of the plane, creating the box or peanut shape. Many barred spiral galaxies show similar structures when viewed edge-on, suggesting this is a common phase in galaxy evolution. Within the bulge, the stellar density increases dramatically. In the outer disk, near the Sun, there might be one star within a few light years, but in the bulge, particularly in its densest inner regions, there could be thousands of stars within that same volume. If Earth were located deep in the bulge, the night sky would be spectacular. Instead of the few thousand stars visible to the naked eye, you might see tens of thousands or more, creating a sky so bright that true darkness would never fall. The bulge is also where we encounter more of the galaxy's globular clusters. These ancient stellar systems orbit the galaxy primarily through and around the bulge, their highly elliptical orbits taking them out into the halo and back. When they pass through the disk, tidal forces from the galaxy's gravity strip away stars from their outer regions, leaving long tails of stars marking their orbital paths. Over time, some globular clusters are completely tidally disrupted, their member stars dispersed into the general stellar population. But the clusters' original association can sometimes still be detected as a stream of stars sharing similar orbits. The chemical composition of bulge stars tells a complex story. While most are metal poor, there's actually a range of abundances, suggesting multiple episodes of star formation and chemical enrichment. Some regions of the bulge show enhanced abundances of alpha elements like magnesium and silicon, which are produced in massive stars that explode as Type II supernovae. This suggests periods of rapid star formation, where many massive stars formed, lived, and died quickly, enriching the gas with their products before lower mass stars had time to contribute their own nucleosynthetic products. As we penetrate deeper into the bulge, we start to notice the galactic bar. Remember, the Milky Way is a barred spiral, and the bar is a substantial structure extending several thousand light-years from the center and containing a significant fraction of the galaxy's stellar mass. The bar is oriented at roughly 27 degrees to our line of sight to the center, so as we travel inward, we wouldn't cross through its center, but rather cut across it at an angle. The bar is a dynamical structure, its shape and orientation maintained by the collective gravity of all the stars and gas within it. Individual stars orbit the galaxy, but their orbits are shaped by the bar's gravitational field in such a way that they spend more time in the bar region, creating the appearance of a solid structure, even though it's made of individual stars on various orbital paths. The bar rotates, but not like a solid body. Its rotation is a pattern speed, the rate at which the pattern of the density enhancement rotates, which can be different from the orbital speeds of individual stars. The bar plays a crucial role in funneling gas toward the galactic center. Gas clouds following near circular orbits in the disk encounter the bar's gravitational field, which perturbs their orbits and removes some of their angular momentum, causing them to fall inward. This is thought to be the primary mechanism for feeding gas to the central regions of the galaxy, where it can fuel star formation and, ultimately, provide material for the central supermassive black hole to accrete. Within the bar and the inner bulge, we encounter the nuclear stellar disk, a distinct component that's flattened, like the main disk, but much smaller in scale. The nuclear stellar disk extends only a few hundred parsecs. A parsec is about 3.26 light years, so we're talking about a structure perhaps 1,000 light years across. This disk is rotating, though not necessarily at the same rate or in exactly the same plane as the main disk. It contains both old stars and evidence of more recent star formation, suggesting a complex history of gas inflow and star formation episodes. The environment in these inner regions is becoming extreme. The stellar density continues to climb. The radiation field strengthens as we're surrounded by ever more stars. If any planets existed in stable orbits here, which is questionable given the gravitational perturbations from passing stars, their night skies would be bright enough to read by. The distinction between night and day would become somewhat meaningless. The increased stellar density has profound implications for any planetary systems that might exist here, where the typical distance between stars in the solar neighborhood is measured in light years. In the bulge, it might be only a fraction of a light year, or even less in the densest regions. This means that close encounters between stars become not just possible, but probable over the lifetime of the galaxy. Such encounters might not result in direct collisions. Stars are so small compared to the spaces between them that even in the dense bulge, actual stellar collisions are rare. But they do result in gravitational perturbations that can disrupt planetary systems, stripping planets from their parent stars or sending them careening into eccentric orbits that might take them far from their suns or plunge them into stellar surfaces. The radiation environment in the bulge is also notably different from the outer disk. With so many stars crowded into a relatively small volume, the ambient radiation field is much stronger. This isn't just visible light, though there's certainly much more of that. There's also an enhanced flux of ultraviolet radiation from hot stars, X-rays from accreting compact objects, and from the hot gas filling the region, and cosmic rays that have been accelerated by supernovae and are trapped in the bulge's magnetic field. Any life that evolved on a planet in the bulge would face challenges that life in the outer disk never encounters, needing to develop robust mechanisms to cope with intense radiation, or perhaps restricting itself to underground environments where planetary material provides shielding. The bulge is also kinematically hot, as astronomers say. This doesn't mean the stars are hot in temperature, though many are, but rather that they have high random velocities. In the disk, stars move on relatively orderly, nearly circular orbits, all rotating in the same direction around the galactic center. But in the bulge, orbital paths are much more diverse. Some stars move on elongated, plunging orbits that carry them from the innermost regions out into the disk and back. Others orbit perpendicular to the disk, spending most of their time in the halo above and below the plane. This velocity dispersion, the spread in velocities, is what supports the bulge against gravitational collapse. In the disk, it's primarily rotation that provides support, with stars moving fast enough in their orbits that centrifugal effects balance gravity. But in the bulge, it's random motion, the kinetic energy of stars moving in all directions, that prevents collapse. This difference in kinematics is related to how these structures formed. The disk formed from gas that settled into the galactic plane, conserving angular momentum and establishing rotation. Star formation from this rotating gas naturally produced stars on circular orbits. The bulge, in contrast, formed earlier and more violently through processes that didn't preserve neat rotation. Early intense star formation, galaxy mergers, and the dynamical evolution of the bar all contributed to creating a population of stars with diverse, random orbits. The chemical abundance patterns in bulge stars reveal a complex history. Early spectroscopic surveys found that many bulge stars are metal-rich, containing as much or more heavy elements than the Sun, despite being much older. This was initially surprising, as it was expected that old stars would be metal-poor, formed before many generations of stars had enriched the interstellar medium. But the high metallicities indicate that star formation in the bulge was intense and efficient in the early universe, rapidly building up heavy element abundances through successive generations of massive stars exploding as supernovae. However, the bulge isn't chemically homogeneous. There's a range of metallicities, and different regions of the bulge show different abundance patterns. Some areas show enhanced abundances of alpha elements, like magnesium and silicon relative to iron, a signature of enrichment by type II supernovae from massive stars. Other regions show lower alpha element ratios, indicating later enrichment by type Ia supernovae, which occur when white dwarfs in binary systems accrete enough material from companions to trigger explosive carbon burning. The complex pattern of abundances suggests that the bulge was assembled from multiple components, perhaps including stars born in the bulge itself, stars scattered from the inner disk by the bar, and stars brought in from merging satellite galaxies. The bar dominates the inner galaxy's structure and dynamics. This elongated distribution of stars extends several thousand light-years from the center, rotating as a coherent pattern at a specific angular velocity, called the pattern speed. The bar's gravity creates a non-axisymmetric potential, meaning the gravitational field doesn't have simple circular symmetry. This creates regions in the disk where orbits that would be stable in an axisymmetric galaxy become unstable. Stars and gas passing through these resonance regions can have their orbits significantly altered, either gaining or losing angular momentum depending on where they encounter the bar. The bar is particularly effective at funneling gas inward. Gas clouds on near-circular orbits in the disk encounter the bar's gravitational field and are torqued, losing angular momentum and falling inward toward the center. This process has built up the gas reservoirs in the inner galaxy and has likely fed multiple episodes of intense star formation in the bulge over the galaxy's history. It may also be the primary mechanism for delivering gas all the way to the central black hole, though even with the bar's help, most gas doesn't make it that far, being converted into stars or heated and driven out in winds before reaching the very center. The bar itself is not a permanent structure on the longest timescales. Bars can form, persist for billions of years, and then dissolve due to various dynamical processes, including the growth of the central bulge or interactions with dark matter. The Milky Way's bar appears to be mature and stable, probably having existed in something like its current form for several billion years, but on time scales of 10 billion years or more. Comparable to the age of the galaxy, bars can come and go, making them transient features of galactic evolution even if they persist for much of a galaxy's lifetime. As we draw within a few thousand light years of the very center, the bar's influence on the structure becomes evident. There's a ring-like feature at certain radii where gas accumulating due to the bar's dynamics forms a concentration of star formation. There are dust lanes aligned with the bar, marking regions where gas clouds on disk orbits encounter the bar and are compressed. The overall structure is complex, three-dimensional, and dynamic, quite different from the simpler, more regular structure of the outer disk. The nuclear stellar disk. That inner component of the disk, extending only a few hundred parsecs, shows evidence of its own distinct history. It's rotating, but not necessarily in perfect alignment with the main disk, suggesting it may have formed from gas delivered to the center by the bar and then settled into its own rotating configuration. The stellar populations in the nuclear disk are mixed, with both old and young stars. Some regions show evidence of recent star formation, perhaps within the last few 100 million years, indicating that gas is still being delivered to the center and converted into stars. Other regions are dominated by older populations, red giants that formed billions of years ago. We also start to encounter more exotic objects with increasing frequency. The inner galaxy has a higher density of neutron stars and black holes, the remnants of massive stars that lived and died billions of years ago. These compact objects are mostly invisible, but some reveal themselves through their interactions with companions or their surroundings. X-ray binary systems, where a neutron star or black hole accretes material from a companion star, are more common in the bulge than in the outer galaxy. The intense gravity of the compact object pulls gas from the companion, heats it to millions of degrees through friction and compression, and causes it to emit copious X-rays. These systems can be incredibly luminous in X-rays, sometimes outshining entire galaxies at those wavelengths, even though the compact object itself might be only a few kilometers across. The gas content in these inner regions, while lower in overall fraction compared to the outer disk, is concentrated into denser structures. The central molecular zone, that region extending a few hundred parsecs from the center, contains enormous gas reservoirs. Giant molecular clouds here can have masses of hundreds of thousands of solar masses, dwarfing their counterparts in the outer galaxy. But despite their mass and density, star formation in these clouds is suppressed compared to what would be expected. The star formation efficiency, the fraction of gas mass converted into stars per unit time, is much lower in the central molecular zone than in the disk. The reasons for this suppression are still debated, but several factors likely contribute. The turbulence in the gas, driven by stellar winds, supernovae, and the dynamical effects of the bar, may be stronger, preventing clouds from fragmenting and collapsing into stars. The magnetic fields which provide support against gravitational collapse may be stronger in the inner galaxy. The tidal shear from the strong and variable gravitational field near the center may disrupt clouds before they can form stars efficiently. Whatever the exact mechanisms, the result is that these massive clouds persist for much longer than similar clouds in the outer disk before being converted into stars or dispersed. When star formation does occur in the central molecular zone, it can be spectacular. The arches and quintuplet clusters those massive young clusters will encounter are examples. These clusters contain thousands of stars, including dozens of very massive stars, all born in intense bursts of star formation from single molecular clouds. The formation of such massive clusters probably requires special conditions. Perhaps the collision of multiple clouds or the compression of an already massive cloud to higher densities. These events are relatively rare, but play an outsized role in shaping the central regions, injecting enormous amounts of energy through stellar winds and supernovae, enriching the gas with heavy elements, and influencing future star formation episodes. As we push ever deeper into the bulge, passing within a few thousand light-years of the very center, we begin to see, faintly at first, but with growing intensity, the glow from the very heart of the galaxy. Not the black hole itself, which emits no light, but the material around it, the stars in the nuclear star cluster, the hot gas in the innermost accretion flows, and perhaps the faint emissions from the black hole's immediate vicinity. We're approaching Sagittarius A, the beast at the galaxy's heart, and the environment is about to become more extreme than anything we've encountered so far. The central Parsec, the nuclear star cluster. As we penetrate within just a few light years of the galactic center, we enter a realm unlike anywhere else in the Milky Way, the nuclear star cluster. This is a dense, spherical concentration of stars surrounding the central supermassive black hole, extending perhaps 10 light years from the center in a roughly spherical distribution. While small by galactic standards, the nuclear star cluster contains approximately 20 million solar masses of stars, packed into a volume that would fit comfortably within the nearest few dozen light years around the Sun in the outer galaxy. The density here staggers the imagination. Near the cluster's center, within a parsec, about 3.26 light years, of Sagittarius A, there are roughly 10 million stars. Compare this to the region within 3.26 light years of the Sun, which contains only a handful of stars, Alpha Centauri and its companions, Barnard Star, and a few others. The nuclear star cluster is millions of times denser than our local neighborhood. What would the sky look like from a hypothetical planet deep within the nuclear star cluster, assuming such a planet could exist in stable orbit? Despite the gravitational chaos, the night sky would be brilliant with starlight. Instead of the few thousand stars visible to the naked eye from a dark site on Earth, you'd see millions. The stars would be packed so densely in some directions that they'd create a nearly uniform glow, like a cosmic Milky Way, vastly brighter and more extensive than the Milky Way band we see from Earth. There would be no true darkness, ever. The combined light of all those stars would be enough to cast shadows and allow you to see colors even in the darkest part of the night. The stellar population in the nuclear cluster is surprisingly diverse. There are old stars, red giants, and red dwarfs that formed when the galaxy was young, billions of years ago. But there are also young stars, hot blue giants, that can only be a few million years old. This was a surprise to astronomers when these young stars were first clearly identified in the 1990s. How could massive, short-lived stars exist so close to the supermassive black hole? Where did the gas come from to form them? And how did it collect there, given the extreme tidal forces that should shred any cloud that wanders too close to the black hole? The young stars are organized into structures. The most prominent of these are the Arches cluster and the Quintuplet cluster, two incredibly dense and massive young star clusters located within about 100 light years of the galactic center. The Arches cluster is particularly extreme. It contains about 20,000 stars packed into a region less than 3 light years across, with a total mass of about 10,000 solar masses. Many of its member stars are massive Wolf-Rayet stars, evolved giants that have stripped away their outer hydrogen envelopes, exposing the helium and heavy elements produced by nuclear burning in their cores. These stars are losing mass at prodigious rates, driving powerful stellar winds that enrich the surrounding environment with processed material. The quintuplet cluster is similar but slightly older and more dispersed. It contains several luminous blue hypergiants, among the brightest stars known. These stars are so luminous, shining with the light of hundreds of thousands or millions of suns, that their radiation pressure actually drives off their outer layers, limiting how massive they can grow. They're barely stable, living on the edge of gravitational collapse inward and radiation-driven explosion outward, dancing on a knife's edge of stability. How these clusters formed is still debated. One possibility is that they formed outside the very center, perhaps tens or hundreds of parsecs away, and then migrated inward through dynamical friction, their large mass causing them to sink toward the galactic center like a heavy ball, bearing settling to the bottom of a jar of honey. Another possibility is that they formed in situ from dense gas clouds that somehow managed to accumulate near the center despite the challenging environment. Current observations can't yet distinguish between these scenarios with certainty, but the debate highlights how much we still have to learn about star formation in extreme environments. There's also a population of young stars in the very innermost parsec, within a light year or two of the black hole itself. These stars, sometimes called the S stars from their catalog designations, follow highly elliptical orbits around Sagittarius A. Some of them pass incredibly close to the black hole, within a few light hours of the event horizon, traveling at speeds exceeding 1% of the speed of light. The star S2, which has been observed for over 25 years, completes its orbit in only about 16 years, allowing astronomers to watch it move through a full cycle and use its motion to measure the black hole's mass with high precision. The S stars are thought to have formed from a gas disk that once existed around the black hole, perhaps a few 100,000 or 1,000,000 years ago. Alternatively, they might be the remnants of a binary star system that wandered too close to the black hole. In such a scenario, one member of the binary would be captured into orbit around the black hole, while its companion was flung outward at high velocity, ejected from the galaxy entirely. This process of tidal disruption of binary systems can explain how stars end up in such extreme orbits. The interstellar medium in the nuclear star cluster is hot and tenuous, kept that way by the intense radiation field from all those stars and by the stellar winds from massive stars, particularly the Wolf-Rayet stars in clusters like the Arches and Quintuplet. These winds inject energy and momentum into the gas, heating it to temperatures of millions of degrees and driving it into outflows. X-ray observations reveal a hot, diffuse plasma filling the region, glowing in the high-energy portion of the spectrum. There are also denser structures, molecular clouds lurking in the central molecular zone, streamers and filaments of gas being pulled toward the center by gravity and compressed by tidal forces. Some of this gas may eventually feed the black hole, though most of it will likely form stars or be heated and driven out by stellar feedback before it gets that far inward. The flow of gas in this region is turbulent and chaotic, driven by the competing influences of rotation, gravity, magnetic fields, radiation pressure, and stellar winds. The nuclear star cluster itself is thought to have formed through a combination of mechanisms. Some of its stars likely formed in situ from gas that settled into the galactic center early in the galaxy's history. Others may have originated in globular clusters or smaller star clusters that spiraled into the center due to dynamical friction, their member stars dispersing into the nuclear cluster as the original clusters were torn apart by tidal forces. Still, other stars may have been delivered to the center by the dissolution of dwarf galaxies that merged with the Milky Way billions of years ago, their stars gradually settling into the deepest part of the gravitational potential. Well, recent spectroscopic studies of stars in the nuclear cluster have revealed details of their chemical composition. Many of the old stars are metal-rich, containing abundances of heavy elements similar to, or even exceeding, those in the Sun. This is somewhat surprising, as you might expect the oldest stars to be metal-poor, formed before multiple generations of stars had enriched the gas. The high metallicity suggests that star formation in the galactic center was rapid and efficient in the early universe, with successive generations of stars forming, and, alternatively, the nuclear cluster may have been built up through the merger of smaller clusters and the dissolution of dwarf galaxies, each contributing their own chemically enriched stellar populations. The dynamical state of the nuclear cluster is complex. The stars are not following simple, orderly orbits. Instead, their motions are influenced by the central black hole, by gravitational interactions with each other, and by the overall potential of the cluster and bulge. Some stars are on nearly circular orbits, while others, particularly the S stars, are on highly elliptical paths. Over time, gravitational encounters between stars cause the velocities to evolve, a process called relaxation. In dense enough systems, this can lead to the evaporation of stars from the outer parts of the cluster and the formation of a dense core in the center, though the nuclear star cluster hasn't yet evolved to that state. As we drift through this dense stellar swarm, we'd be witnessing stellar evolution on fast forward compared to the outer galaxy. Massive stars are forming, living, and dying on timescales of just millions of years. Supernovae explode, briefly outshining all the other stars in the cluster combined, their blast waves rippling through the surrounding gas, compressing it and perhaps triggering new episodes of star formation. White dwarfs accumulate, the inert remnants of dead sun-like stars, their electron-degenerate cores supported against further collapse only by quantum mechanical effects. Some of these white dwarfs are in binary systems, accreting material from companions, occasionally erupting in nova explosions as the accumulated hydrogen on their surfaces ignites in a runaway thermonuclear burn. There are neutron stars here too, though most are invisible, dark, and isolated, having long since turned off but some remain active, either as pulsars if their magnetic fields and rotation axes are aligned favorably, or as accreting X-ray sources if they have companions from which they can pull material. And there are black holes, stellar mass black holes, formed from the collapse of massive stars. These are incredibly difficult to detect unless they have companions or are actively accreting gas. But statistical arguments suggest there should be thousands of them in the nuclear cluster, sinking toward the center due to mass segregation, the tendency for more massive objects to settle deeper into the gravitational potential. And at the very center, dominating everything, is Sagittarius A. We can't see it directly yet. It's too small, too dark against the background glow of stars, but its influence is everywhere. It shapes the orbits of the nearest stars. It pulls on the surrounding gas, stirring it, heating it. It's the anchor point around which the entire galaxy rotates, the gravitational center toward which everything, ultimately, is falling. As we draw closer, preparing for our final plunge into the very heart of darkness, the true nature of this cosmic monster begins to reveal itself. Sagittarius A, the heart of darkness. At the exact center of our galaxy, in the constellation Sagittarius as seen from Earth, lies an object so extreme that it challenges our understanding of physics. Sagittarius A, abbreviated SGRA, and pronounced Sagittarius A star. This is the supermassive black hole that anchors the Milky Way, a gravitational abyss containing approximately 4.3 million times the mass of our Sun, all compressed into a region smaller than Mercury's orbit around the Sun. Black holes are perhaps the most conceptually difficult objects in all of astrophysics. They're not holes in the ordinary sense, not empty regions of space. Instead, they're regions where gravity has become so intense that space-time itself is catastrophically warped. At the heart of every black hole lies a singularity, a point where density becomes infinite and our current theories of physics break down. But we can't see the singularity. It's hidden behind an event horizon, a one-way boundary surrounding it. The event horizon is not a physical surface. There's nothing there, no barrier or membrane. It's simply the point of no return, the boundary beyond which escape becomes impossible. Once you cross the event horizon, all possible paths through space-time lead inward, toward the singularity. You can no more escape from inside a black hole than you can travel backward in time. Light itself, the fastest thing in the universe, cannot escape once it's crossed that boundary. Hence the name, black hole. For Sagittarius A, with its 4.3 million solar masses, the event horizon has a radius of about 12.7 million kilometers. That's about 8.3 million miles, or roughly 30 times the radius of the Sun. It sounds large, and it is by terrestrial standards, but remember, we're talking about 4 million suns worth of mass. A typical star like the Sun has a radius of about 700,000 kilometers. If you could somehow compress the Sun down to a black hole, it would have an event horizon only about 3 kilometers across. The fact that Sagittarius A's event horizon is so much larger is only because it contains so much more mass. Black holes are actually quite compact for their mass. A black hole with the mass of Earth would have an event horizon only about 9 millimeters across, smaller than a grape. The discovery of Sagittarius A as a supermassive black hole was a gradual process spanning decades. In 1974, radio astronomers Bruce Ballack and Robert L. Brown identified a compact radio source at the Galactic center, but its nature was unclear. Over the following decades, observations at various wavelengths revealed that this object was associated with the galaxy's dynamical center, the point around which everything orbits. But the conclusive evidence came from tracking the motions of stars near the galactic center. Starting in the early 1990s, 2 teams of astronomers, one led by Reinhard Genzel and the other by Andrea Ghez, began long-term monitoring programs to measure the positions and velocities of stars near SGRA. Using adaptive optic systems on large telescopes to compensate for the blurring effects of Earth's atmosphere, they achieved angular resolutions fine enough to track individual stars as they orbited the center. Over years and then decades, they watched these stars move, mapping out their orbital paths with increasing precision. The results were unambiguous. The stars were orbiting something massive and compact at the location of SZRA. By measuring the periods and semi-major axes of the orbits and applying Kepler's laws, they could determine the mass of the central object. The answer kept coming back the same, about 4 million solar masses, and the stars were passing within just a few light hours of this mass, close enough that it had to be incredibly compact. The only known object that could have 4 million solar masses confined to such a small volume is a supermassive black hole. For their discovery, Genzel and Ghez were awarded the 2020 Nobel Prize in Physics, which they shared with Roger Penrose for his theoretical work on black holes. The most dramatic confirmation came in 2022 when the Event Horizon Telescope collaboration released the first direct image of Sagittarius A. The Event Horizon Telescope isn't a single instrument, but a network of radio telescopes spread across the globe, from Hawaii to Chile to the South Pole, all linked together through a technique called Very Long Baseline Interferometry to act as a single virtual telescope the size of Earth. By combining observations from April 2017, taken by 8 different observatories, the collaboration produced an image showing a dark central shadow surrounded by a bright ring of emission. This image perfectly matched the predictions of general relativity. The dark shadow represents the region of space where photons can't escape, essentially the event horizon plus a slightly larger region where photons are on orbits that will eventually fall into the black hole. The bright ring is emission from hot gas orbiting just outside the event horizon, accelerated to tremendous speeds, and heated to billions of degrees by friction and magnetic field interactions. The light from this gas is bent by the black hole's intense gravity, creating the characteristic appearance, a shadow surrounded by a bright ring. The gas around Sagittarius A is not uniform or static. It's turbulent, variable, with hot spots and blobs that rotate around the black hole and then either fall in or are flung outward. This variability makes imaging SCAR A challenging. Unlike M87, the supermassive black hole at the center of the elliptical galaxy M87, which the Event Horizon Telescope imaged first in 2019, SGRA is constantly changing on timescales of minutes. The imaging team had to develop sophisticated techniques to average together observations and account for this, essentially producing a long exposure image that captures the black hole's average appearance. Despite being the closest supermassive black hole to us, only about 26,000 light-years away, Sagittarius A is actually remarkably quiet. Many other galaxies host much more active black holes, objects that are voraciously consuming gas from their surroundings and shining brilliantly across the electromagnetic spectrum. These active galactic nuclei can outshine their entire host galaxies, pumping out more energy than hundreds of billions of stars combined. SGAR A, in contrast, is barely glowing. It's accreting material at only a trickle, probably swallowing only a tiny fraction of a solar mass per year, maybe less. Why is SGAR A so quiet? It's partly a question of fuel supply. While there's plenty of gas in the galactic center region, most of it has too much angular momentum to fall directly into the black hole. The gas needs to lose angular momentum somehow before it can spiral inward across the event horizon. There are several mechanisms that might do this, including magnetic friction, turbulence, and gravitational interactions. But apparently, they're not very efficient in the Milky Way's current state. Most of the gas that does make it to the inner regions is either ejected in winds or settles into some kind of quasi-stable flow that doesn't decrete rapidly. Observations suggest that SGAR A hasn't always been so quiescent. There's evidence for past outbursts, periods when it was much more active. X-ray echoes, essentially light echoes, but in X-rays, have been detected from molecular clouds near the galactic center. These echoes indicate that SGAR A experienced a bright X-ray outburst only a few hundred years ago, perhaps around the year 1700 as measured in Earth time. The black hole was briefly millions of times brighter than it is now before fading back to its current low level. What triggered this outburst? Perhaps a gas cloud, or even an asteroid or comet, fell into the black hole, providing a temporary feast. The environment immediately around Sagittarius A is extreme beyond imagining. The gravitational field is immense. Tidal forces, which increase closer to the black hole, would rip apart any ordinary object that ventured too close. There's actually a boundary called the tidal disruption radius, where the tidal forces become strong enough to overcome the self-gravity holding an object together. For a sun-like star, this radius is about 100 times the event horizon radius for SGRA, so a star would be shredded long before it reached the event. The process of tidal disruption is spectacular. The star is stretched into a long stream, with half the material flying outward and half falling back toward the black hole, creating a bright flare as the returning material heats up and emits light before vanishing across the event horizon. Close to the event horizon, space-time is wildly distorted. Light rays follow curved paths, bent by the gravitational field. Time itself runs slow. If you could hover just above the event horizon, held there by some impossibly powerful rocket, and watch a clock far from the black hole, you'd see it ticking faster and faster from your perspective. Meanwhile, an observer watching you from far away would see your clock ticking slower and slower, approaching a standstill as you neared the horizon. At the event horizon itself, time for you from the distant observer's perspective would stop entirely. Of course, you wouldn't perceive this yourself. From your perspective, time would pass normally. But the universe outside would seem to speed up. Stars would race through their life cycles, and eventually you'd see the far future of the cosmos before you finally crossed the horizon. Actually crossing the event horizon would be one way. There'd be no coming back, no sending signals out, nothing. But the crossing itself, for an observer falling in, wouldn't feel like anything special. There's no barrier, no sensation. You just pass through, and only by looking back would you realize you could no longer see anything outside. And even that view would be distorted, compressed into an ever-shrinking circle behind you, as more and more of your view becomes filled with the blackness ahead. Eventually, you'd be pulled into the singularity. For a black hole as large as Sagittarius A, this would take a surprisingly long time. From the infalling observer's perspective, perhaps many minutes or even hours from the horizon to the singularity. But those final moments would be characterized by ever-increasing tidal forces, stretching you lengthwise and compressing you transversely in a process sometimes called spaghettification, until ultimately you'd be torn apart into a stream of atoms, and then those atoms themselves would be torn apart before finally reaching the singularity where physics as we know it ceases to apply. But we won't cross the horizon on our journey. We'll stay safely outside, observing from a distance. Even so, the view would be extraordinary. The black hole itself would appear as a perfectly black circle, darker than the darkest night, completely silent and still. Around it, we might see the glow of accreting gas though, since Sagittarius A is not very active. This might be quite faint. The ring of emission seen by the Event Horizon Telescope is primarily in radio wavelengths and is quite tenuous. In visible light, the immediate vicinity of the black hole might actually not be very bright, with most of the light coming from the surrounding stars of the nuclear star cluster. What would be most striking is the lensing effect. The black hole's gravity bends light passing near it, acting like a gravitational lens. This would create multiple, distorted images of objects behind the black hole. Stars directly behind the black hole would appear as a bright ring, an Einstein ring, around the black hole's silhouette. More distant stars would be magnified and distorted in complex ways, the entire stellar background would be warped, stretched, and folded by the gravitational lensing, creating a funhouse mirror effect on cosmic scales. Looking around, away from the black hole itself, we'd see the inner parsec of the nuclear star cluster. Stars everywhere, incredibly dense. The S-stars whipping past on their elliptical orbits, some completing full circuits in just a few years. Farther out, the slower-moving stars of the general cluster population. And beyond that, the glow of the galactic bulge, containing billions of stars, all orbiting this central point, this darkness at the heart of our galaxy. It's a humbling sight. This monster black hole, while enormous by any reasonable standard, is actually quite small compared to the galaxy it anchors. The event horizon is only about 30 times the radius of the Sun. The influence radius, the region where the black hole's gravity dominates over the surrounding matter, extends, perhaps, a few light years. Beyond that, the galaxy's overall gravitational field takes over. Sagittarius A is like a tiny seed at the center of an enormous tree, insignificant in size, but crucial to the structure. And yet, despite being only 4 million solar masses, tiny compared to the billion solar mass behemoths lurking in the centers of some galaxies, Sagittarius A plays a crucial role in the galaxy's evolution. Its gravity anchors the inner galaxy, the energy released by past episodes of accretion, while a tiny fraction of what active galactic nuclei produce, still influence the surrounding gas, heating it, ionizing it, perhaps regulating star formation in the central regions. The black hole is both a sink, consuming any matter that wanders too close, and a source, driving winds and outflows when it feeds. It's an integral part of the galactic ecosystem, connected through gravity and gas flows to the larger structures surrounding it. The return journey changed perspectives. Our time at the galactic center must eventually end. We've witnessed the heart of our galaxy, seen the supermassive black hole and the dense stellar environment surrounding it, looked upon sights that few humans have even imagined. But now we must begin the long journey home, back through the 26,000 light years separating us from Earth, back through the bulge and the spiral arms, returning to our quiet corner in the Orion Spur. The journey back would, in many ways, be a reversal of our inward trip. We'd watch the stellar density gradually decrease as we moved outward from the nuclear cluster, passing back through the bulge with its old stars and complex structure, crossing the galactic bar region, and eventually emerging into the thinner disk. We'd pass through the same spiral arms, perhaps from slightly different angles depending on our exact path, seeing familiar star-forming regions from new perspectives. But the journey wouldn't feel the same. It couldn't. Having seen the center, having witnessed the galaxy's heart, we'd carry that knowledge with us. Every star we passed on the way back would now be understood not in isolation, but as part of a vast, interconnected system. That star is part of a stream of stars that once belonged to a globular cluster, now torn apart by tidal forces. This nebula's gas was enriched by supernovae in the inner galaxy and transported outward by galactic winds. Those stars there are members of an open cluster that formed recently from gas that was once cycled through the nuclear regions. We'd see the galaxy now as a single, coherent system, not a collection of separate objects. The spiral arms are not independent structures, but manifestations of density waves that propagate through the disk. The stars we pass were born from gas that has been recycling for billions of years through stars and back to gas, back to stars again, enriched in heavy elements with each cycle. The galaxy is alive in a sense, not with biological life, but with an ongoing process of transformation, matter flowing from one state to another, energy released, and redistributed, structure emerging from chaos through the organizing principle of gravity. The journey would also give us a new appreciation for how unique our place in the galaxy is. We live in a relatively quiet region, far from the intense radiation and gravitational chaos of the center, far from the violent star-forming regions of the major spiral arms. Our environment is stable enough that a star like the Sun could maintain a planetary system for billions of years without having planets stripped away by close stellar encounters. It's enriched enough in heavy elements that rocky planets can form. It's protected enough from radiation that life can evolve on at least one of those planets without being sterilized. This is not to say that our region is special in a cosmic sense. There are probably billions of similar regions in the galaxy, quiet neighborhoods where conditions are conducive to the long, slow evolution of stable planetary systems and, perhaps, life. But it does highlight how the galaxy creates different environments in different regions, and how the particular environment we happen to inhabit has shaped everything about our existence. As we traverse outward through the disk, we might appreciate anew the spiral structure and what it represents. The spiral arms are not static. They're transient, lasting perhaps a few 100 million years before they wind up too tightly and dissipate, with new density waves forming to replace them. The galaxy we see now is not the galaxy of a billion years ago, and it won't be the galaxy of a billion years hence. The structure evolves, shaped by internal processes like the bar and spiral arms, and by external influences like the gravitational pull of the large and small Magellanic Clouds, our satellite galaxies, and the distant approach of Andromeda, the nearest large galaxy, which will collide with the Milky Way in about 4 billion years. That collision, when it comes, will transform both galaxies. Stars won't actually collide. They're too far apart, the space between them too vast. But the gravitational interactions will scramble orbits, flinging some stars into the intergalactic void and sending others plunging into the center. Gas clouds will collide, triggering intense bursts of star formation that could briefly make the merged system shine much brighter than either original galaxy. The two supermassive black holes will spiral together and eventually merge, creating a single black hole with the mass of both and releasing gravitational waves that will ripple through space-time across the universe. Out of the chaos will emerge a new galaxy, probably an elliptical rather than a spiral, a quiet collection of old stars in a spheroidal distribution, its star-forming days mostly behind it, slowly fading as its stars age and die with no new generations to replace them. But that's billions of years in the future. For now, we journey through the galaxy as it is, in its current spiral phase, still forming stars at a rate of a few solar masses per year, still dynamic and evolving. As we approach the outer disk and draw closer to our starting point, the sun begins to brighten among the stellar background. At first, it's just one more star, no more remarkable than any other. But gradually, as we approach, it distinguishes itself the one star we know more intimately than any other, the one that's been our constant companion throughout the existence of our species. And long before, finally, we return to the solar system, that tiny bubble of space dominated by the sun's gravity and light. The planets swing into view, familiar patterns restored. Mars, Jupiter, Saturn with its rings, the outer ice giants, the asteroid belt, that rubble left over from the solar system's formation, and finally, Earth, that small blue world, so insignificant, from a cosmic perspective, barely a speck in the galaxy, and yet home, the cradle of humanity, the place where consciousness arose and wondered about the universe. Conclusion. Let yourself settle back now, allowing your breathing to slow and deepen, feeling the weight of the journey lift from your shoulders. We've traveled together through 26,000 light-years of space, from our humble solar system to the blazing heart of the Milky Way and back again. We've witnessed wonders beyond imagining, stars being born in vast nebulae, ancient clusters of stars older than the galaxy itself, the supermassive black hole that anchors our cosmic home. And now we return, changed by what we've seen, carrying with us a new understanding of our place in the grand architecture of the universe. The galaxy seems almost impossibly large. 26,000 light-years is a distance our minds cannot truly comprehend. And yet, vast as it is, the Milky Way is just one galaxy among hundreds of billions in the observable universe. Beyond our galaxy lie others, some larger, some smaller, each with its own history, its own population of stars, perhaps its own worlds where other forms of life wonder about their own cosmic homes. But here's the beautiful paradox at the heart of the cosmos. While we are vanishingly small, almost insignificant specks of matter in this vast universe, we are also, in a very real sense, the universe becoming conscious of itself. The atoms in your body were forged in the hearts of stars that died before the sun was born. You are quite literally made of stardust, ancient matter that has traveled through the galaxy over billions of years, eventually finding its way to Earth to form the molecules that make up your cells, your neurons, your consciousness, the calcium in your bones, the iron in your blood, the carbon that forms the backbone of every organic molecule in your body. All were created inside stars and then scattered into space when those stars died, enriching the interstellar gas that eventually collapsed to form the sun and Earth. You are not separate from the galaxy, not an observer standing apart from it. You are part of it, connected through an unbroken chain of events, stretching back to the galaxy's birth 13 billion years ago. This journey we've taken together, while imaginary in its details, represents a kind of truth about our relationship to the cosmos. We are children of the galaxy, born from its material, shaped by its evolution. The peace we can find in this understanding is profound. We are both tiny and essential, temporary and connected to something eternal. Our individual lives, while brief, are threads in a great cosmic fabric that stretches across time and space. As you drift towards sleep now, or simply rest in this calm state of contemplation, let the scale of the universe bring you comfort rather than anxiety. The galaxy has existed for billions of years before you and will continue for billions more after. It has witnessed countless cycles of birth and death, stars forming and dying, matter transforming from one state to another, energy flowing and redistributing according to the laws of physics. In all that time, in all that vastness, you are here now, conscious, aware, able to contemplate your own existence and the nature of the cosmos that gave rise to you. Tomorrow the sun will rise, just as it has for billions of years, just as it will for billions more. The galaxy will continue its slow rotation, making no distinction between night and day, between one moment and the next. And you will be part of it, as you have always been, as you always will be, even after the particular arrangement of atoms that makes up your current body has dispersed and rejoined the cosmic cycle. Let that thought comfort you. You are not alone. You are not meaningless. You are part of something greater, something ancient and beautiful, something that transcends the worries and concerns of daily life. The galaxy holds you, as it holds all things, in the gentle but inexorable pull of gravity, in the flow of matter and energy, in the evolution of complexity from simplicity, consciousness from unconsciousness. Rest now. Let your mind drift like a spacecraft between the stars, peaceful and calm, knowing that you have seen the center of the galaxy and returned, that you carry that knowledge with you, that vast perspective that puts everything in its proper place. You are stardust, conscious and wondering, and that is enough. Good night, fellow traveler. May your dreams be filled with stars.